Okay. Good evening, guys. Hope everything's going well. And this is my third time trying to record this. Last two times I didn't want to actually record it after I was all done. Or save it, I should say. Recorded it fine. Okay, so I'm going to try doing this in 4 shorter pieces, so hopefully this works. Please read this first story on the first page of chapter 4, starting about floods, famines, and all that stuff. The fact is, our climate is changing, and it is going to have an effect on us, and we are not completely sure what that effect is. So let's get going here. Vocabulary. I'm going to go through a lot of this. Climate, weather, troposphere, stratosphere, mesosphere, thermosphere, exosphere, and ozone layer. And I swear, if my child needs to hear me say this a third time or a fourth time, he'll know this really well. Okay, really quick. Atmosphere. From the Earth up to space. We have troposphere, stratosphere. Your good ozone layer is in your stratosphere. That's the one that blocks UV light so we don't become little pieces of skin cancer. Mesosphere, thermosphere, exosphere. If you want a mnemonic to remember which way they go, I use Tiny Soldiers March to Earth. T is for troposphere, S is for stratosphere, M is mesosphere, T is thermosphere, and then the E is exosphere. So it can help you keep them in the order. The fact is, the most two important are, of course, the troposphere, where we are in the troposphere, and then the stratosphere, where a lot our ozone layer is and stuff. So most of our climate weather all happens here in the troposphere and stratosphere, and most everything we're concerned about occurs there. Okay, so what is climate? Climate is determined by temperature and precipitation patterns, and these are long-term temperature and precipitation patterns. What is occurring outside right now, that it is slightly cloudy, no rain, and kind of warm and sunny, that is weather. Our climate is, hundreds of years of weather, what that averages out to be. So here in Florida, we're warm and humid, or wet. We have quite a bit of precipitation, we have relatively warm temperatures, so we're kind of more tropical or subtropical compared to if you go up north. So your temperature and your precipitation patterns determine your climate, and that determines your biome. Actually, that determines the plants that grow, and the plants that grow in an area is the biome. So biomes are all based on plants. The climate determines the plants, but they're based on their plants. Okay, so why do different areas have different biomes and different climates? Biggest reason is actually our Earth's tilt. The fact is, the Earth's tilt causes uneven heating for 2 reasons. First, the angle over which the light shines. If you have a flashlight and you point it straight down, you're out hiking or something, you're going to get this nice little intense circle of light. It's going to be bright, it's going to be over a small area. Where if you point it out in front of you, you're going to get that same amount of light over a greater area. So if you spend the same amount of energy over a greater area, that's going to decrease its intensity over these areas. So this is going to be at your equator. You're going to get really bright, hot sun, and then as you go north, it gets more and more angled, and therefore over a greater area, so it decreases its intensity and actually causes it to be cooler. So as we get towards the poles, that's what's happening. The other thing is the distance through which the distance through the atmosphere that it has to travel, and I'll show you in the picture on the next page. So if you turn to the next page in your book, you'll see here you have incoming light rays, and again here at the equator they go through a short distance of the atmosphere, and they're very concentrated in a small area, where here the light's coming through, it goes through a much greater distance, and it's over a greater distance or greater area, and so that's going to cause this to be less intense and therefore less hot, where this is going to be much more intense and more hot. Okay, a few vocabulary words you need to know, and most of these I'm going to go over. Albedo, I'll talk about that in just a second. Adiabatic cooling and adiabatic heating, I'll go over those. Intertropical convergence zone, the ITCZ, I'm not going to go over that, so make sure you read that, and I'll go over the Coriolis effect, either in this video or the next one. Okay, since I'm going to cut this video a little shorter than the others, and hopefully it will actually record it this time. Okay, 3rd time's the charm, right? Okay, albedo. Albedo is the reflection of solar energy. How much solar energy is reflected? White things, ice, snow, reflect a lot more energy back, the sun's solar energy back into space, into the atmosphere, than dark things absorb. So things like ice and snow have a high albedo, very high albedo. About 80 to 90% of the sun's solar energy is reflected back to space, which actually ultimately helps keep snowy, icy areas even colder. So that actually helps to work that thing, although we might be at a tipping point with our polar area, because if you get rid of the sun or this ice, then more of that heat is going to be absorbed, which means the area is going to get warmer, which means more ice will melt, which means more heat is absorbed, and so on and so forth, and we got a positive feedback. Gotta love our feedback loops. Okay, one of the biggest things is we have convection cells or convection currents in our atmosphere, and that moves our air around, and our air moving around changes temperature and precipitation patterns, and we're going to talk about these. There's basically 4 things that cause this. The density of the air. Dense air, more dense air is going to sink, less dense is going to rise. The water vapor capacity, which I'm not really going to talk about very much. Hang on, I got it. My ear itches. Water vapor capacity. Hot air can actually hold more water vapor, which is why in the summer, after our nice hot days and we get those rains, it's very hot and humid inside. That's because warm air, hot air can hold more water vapor. Cold air can't. It will condense and rain. Okay, adiabatic cooling, adiabatic heating. We're going to talk more about these, but in just a second, and then I'll talk more about latent heat release. But those are the things that ultimately determine our air cycles, and these cycles that go up and down. And I'll show you a picture in a sec. So adiabatic cooling, what happens is air rises, there's less pressure up in the atmosphere the higher you go, that's why your ears pop in the plane, and which means you're increasing your volume, your air is moving further apart, and as your air molecules move further apart, it actually causes the temperature of your air to drop. It gets lower, it gets colder. In adiabatic heating, it's the actual opposite. The air is sinking. As the air sinks, it increases pressure, which means it's decreasing volume, which means the air molecules are getting closer together and actually causes an increase in temperature or for the air to get hot. Okay, latent heat release. This is a pretty cool thing. As water vapor condenses and changes from a gas to a liquid, it actually releases heat. That process of changing actually releases heat, which is going to cause your air to get warmer and rise, because again, hot air rises. Okay. Oh, come on, page. Okay, so here's a convection cell. Here's one. This is the Hadley cell. This is occurring at the equator and between basically and 30 degrees north and south. What happens is here at the equator we get very warm, wet from all that transpiration of all the rainforest plants and stuff, the trees. We get very humid hot air. Humid hot air is actually less dense. It's going to rise. As it rises, it goes into adiabatic cooling. So the warm humid air is going to rise. It's going to go through adiabatic cooling, which means we're going to get clouds and rain. So it's literally going to cool off to the point where, again, colder air can't hold as much water, so it's going to condense and it's going to rain and it's going to drop all that water. When it gets up here to the top of the Hadley cells, it's dry cold air. Well, cold air is more dense, so it's going to sink, and it actually comes down. It comes down here at about 30 degrees north and south of the equator. The fact is, though, as it comes down, it goes through adiabatic warming or heating. So your cold dry air starts to come down, goes through adiabatic heating, makes it hot dry air, and what do you know? We get deserts at our 30 degrees north and south. Those are our subtropical deserts. Those are the deserts you think about when you think of a desert, like out in the western United States. Okay, so that's one of our cells. We'll talk about the others in just a minute. One other thing I mentioned was the Coriolis effect. The Coriolis effect is a deflection of things that basically come over the Earth's surface due to the Earth's rotation. So if you see this little black line here, that is the direction that these cells, the Hadley cells, the bottom of the Hadley cells, should be following. Should be coming basically straight down from the deserts to the equator, then back up and then back down and keep going that way. But because of the Earth's rotation, it's actually deflected at about a 45-degree angle. So it actually comes this way and it goes off at an angle. Those together, that deflection and all that movement, the deflection affects winds and your water currents. We'll talk about water currents in a minute. But that deflection ultimately results in our winds. So we get our trade winds north and south of the equator, and then we have our polar cells that create our polar easterlies, those winds at our poles. And then in between we have very weak cells. These are your convection cells again. Hadleys are here, polar easterlies are here, or polar cells are here. And then in between we have where the green arrows are. Those are actually the Ferrel cells. Ferrel cells are rather weak cells, but they do help create the westerlies. So trade winds around the equator, and then the westerlies north and south of those, and then at the poles we have the polar easterlies. And that's our wind pattern. Wind blows across water, which moves the water. Now the water should go at a 45 with the wind, but because of the Coriolis effect, rather than going at a 45 with the wind, it actually turns and goes parallel with the latitudes. So it actually runs along the equator, which creates our currents. And we'll talk about currents in just a minute. Actually, let me just do seasons, and then I'm going to end this, and hopefully this will record this time. Okay, last thing for this one, and we'll talk more about currents on the next one and El Nino and stuff. Seasons has nothing to do with the distance we are from the sun, because actually we're closest to the sun in our winter. Has to do again with the tilt. So in the winter, our winter, northern hemisphere, southern hemisphere, we are opposite seasons. So we are in our winter because we are tilted away from the sun. As we go over here and nobody's tilted to the sun, we're kind of parallel, we're into spring or fall, and then depending on which hemisphere you are, and then as we in the northern hemisphere are tilted more towards the sun, now we're into our summer, and then we're into our fall, back to winter, spring, summer, fall, and so on. So here we are not tilted towards or away, we're kind of all equal. And then here we're tilted away, it's our winter. Here we're tilted towards, that's our summer. Okay, so let's see if this sings. Have a good night. I will do part 2 soon.